Welcome back to Fullerton College Pre-Press Print 75 and 77 combined course. This is Professor Ben Hewitt. Today we are looking at PIA Trainee Manual, Section 1.3, Digital File Basics. And yes, I have figured out a way to shoehorn in my dorky obsession with historic aircraft into this particular chapter. Actually, it's a pretty good analogy for what we're doing here. I'm sharing with you a recognition chart, which is a thing that you always put out there when it's wartime and there are airplanes involved. You want your people on ships, on land, and planes to be able to look at the skies and see the airplanes flying over and know whether or not they should shoot at them. It's a big deal. In fact, a lot of famous markings, if any of you know about anything about planes, especially older World War II planes, you might recognize the black and white invasion stripes painted on Allied planes during the Normandy invasion in 1944. You might recognize. You might also remember a bunch of yellow painted front ends of German planes of a slightly earlier part of that war, all to make it easier for people on the ground and on ships looking up at the skies to know whether or not they should be shooting at that plane. In fact, it goes more than that too. If you start looking at the silhouettes and recognizing what they look like and learning to hear the sounds of their engines, which for me is the fun part of watching the skies near the airport that I live by that flies all the fun historic planes, you kind of understand a bit about the plane from the sound it makes, from what it looks like, from the different angles you can see it at, and you become an expert at recognizing these things quickly. And that's kind of really what I want to do with you guys with this chapter and with digital file types. Although we're not looking at airplane silhouettes and listening to engines, the biggest thing we're going to look for is file extensions, the .pdf or the .jpg at the very end of a file name that lets you know what you should expect from that file. In this chapter, the PIA would love us to understand the difference between bits and bytes and understand the different types of software files. There will be more things in the future in this class and in other classes that tell you in much more excruciating detail how these different files go. I particularly like discussing how the JPEG works because it's not entirely straightforward, and I find these things fascinating. And we're going to look at the common file extensions. That's our spotting chart here at the end of the chapter. This may be 2 videos, it may not be. We're going to find out. Nuts and bolts. So previously, before digital formats, everything was stored analog. If you listen to music, you played on a vinyl record, an LP, and you'd have a front and a back, and there'd be a needle that scratches the surface that translates sound vibrations picked up on a microphone into physical vibrations of a needle that scratched in and etched the sound into a physical format. And to play it back, you put it on a record player, and the same squiggles that the first etching needle made is then picked up by a head full of little tiny needles that then vibrate at the same frequencies as the little scratches that were made on the surface of the record. And that actually, even without electronic components in the earliest phonographs, that physical little tiny vibrating needle makes the right sound, gets amplified up the giant petunia bell shape um, amplifier, and that brings the sound back out from a analog physical format into a audio sound. It turns vibrations into a physical shape and then reiterates that shape back into vibrations through another media. Audio cassettes use magnetic encoding on a recording on a very long strip of tape, and you had to rewind them with pencils. I remember this quite a bit growing up. I had cassette tapes of my favorite musics. And after a while listening to them, you start to wear out the magneticness of that tape, and you have to replace it because you can actually listen to it to death. Photographic negatives, they were actually developed onto little pieces of film, plastic film, and you could use those negatives to make more prints of the photo later in the future. Printouts, slides also. Slides were huge, and slides were a way of actually storing print files. I know we've talked in this course about how printing used to be done manually with photographs, and the USB thumb drive that you guys carry around these days. Well, when I was a kid, my dad always had, he had a whole closet full of these things. I mean, tons and tons of them. Slide carousels. And they looked something like this. Each one of those little white things in that round carousel is a slide, and the slide is a transparency with basically a photo positive or negative, depending on what you're storing on it. And this is a way of reducing large things into small things. You can also use microfilm, and you guys may never experience this, but when I was in college, I had to use microfilm and microfiche, another version of it, which was very small film where they were able to reduce large documents into very small slides and put them on a long strip of thing. In fact, there's a lot of old spy movies. There's always some double agent sneaking through trying to steal somebody's microfilm so they can stick it in a hole in their shoe and transport it across the Berlin Wall to show, well, it depends which movie and which side you're watching about. But the point is, it was all physical storage done through optical means. I don't really need to tell you that today most things are stored digitally. Even photography no longer really uses film unless you're doing something very specifically art house with your photography. Most photographers, even the professional ones, especially the professional ones, have gone digital because everything that wants to get produced, all the equipment to produce them has gone digital. So welcome to the digital world, guys. So what makes a file digital? If it's based out of digital information. What is digital information? Why, I'm so glad you asked. Digital information is a series of binary numbers, ones or zeros, and every single bit, a bit is a single piece of digital information. A bit is a single light switch. In the earliest computers that that the Woz and the other guys were building in their garages in Silicon Valley in the 70s, these computers, some of them actually physically had little tiny toggle light switches on the outside that you flipped up and down in sequence to manually enter digital byte information byte. I should have said bit. I'm so used to bytes because it's been so long since a single bit was ever important. But you would actually flip manual things on and off. Let me see if I can show you this. So here's a very short clip of somebody else's video. Hopefully I don't get in a lot of trouble here by using this. But this is a circuit board built as a primitive computer. Early computers were just this. Oh, it's not playing, is it? There we go. You'd press switches, and the switches would activate different pulses to go between the different transistors and resistors. I don't know enough about electronics to talk about this thoroughly. There are videos about this. But this is basically processing a single bit of information. It's either one of those lights or the other light. Anyways, so that's a single bit, is a single switch. Modern computers use billions of switches a second, and they are able to use all of these just little offs and ons, ones and zeros, to calculate very complicated numbers and do a lot of complicated work. Everything you do in Photoshop is simply your computer calculating a ton of values for all those pixels, and all those pixel values are based off of ones and zeros. 1 bit is a single on-off. 1 byte is 8 bits. Why 8? It's base 2. I'm not as good of a mathematician as I was in high school, so I can't tell you the exact numerical reasons for all of this, but I can tell you the significance is using base 2 math, you get, well, I guess you're cubing it. You get 2, 4, 8, 256. It just keeps going. It's an exponential growth function using base 2. So 8 bits has 256 possible values that can be expressed using 8 switches. And one of those is all off, all zeros, and that number is 0. And all ones, 1, 1, 1, 1, 1, 1, 1, 1, makes up 255. So including all on and all off, you have 256 possible numbers stored in a single byte of information. So on the computer, this also then, we've been recently updating all the systems around the world to 32-bit and now 64-bit operating systems. And what that means is how many bits of information are used as the general basis of what's going on. And what's going on is more than just how many colors you can put on your screen by using different RGB values. The number of zones you can have on your network, the amount of information you can use to define any given color, anything on your computer comes down to how many bytes of information or how many bits you're able to give it. So if you think about it, 8-bit color uses 1 byte to come up with a single shade of a color for a pixel. So 8-bit games like the early Nintendo's OG Mario, that's 8-bit. That means it has 256 colors available to the system that it can show because it has that much memory devoted to that, showing you that color. You can also be used to represent different characters. You can have 256 letters in a font if you use a single byte of information, and we'll get to that in a minute too. The units of data storage, stuff you probably already know, and you might also be able to look quaintly at this and say, I know exactly when this was made, because when they made this, a very common number that we use nowadays wasn't really thought of as a thing that you would need. So you have your bit, which is a single on-off. Your byte is 8 of those. A kilobyte is 1024 bytes because 1024 is actually a power of 2 function. That's why it's not just 1000. A megabyte is not exactly 1 million bytes. It's rounded to a million. It's a little bit more, and I could look it up for you if you like to find out the exact number, or you could Google it yourself. How many bits or bytes are actually in a megabyte? Because it's over 1,000. And then it jumps here to terabyte, which is 1,000,000,000 bytes. What they never thought of when they first wrote this curriculum, and they should have updated this slide, maybe I will someday, is that we would ever use gigabyte as a thing. When would we ever say giga? In fact, there's a fun goof in a movie that I like based off of this, and I won't share the video for copyright reasons. If you guys have seen the original Back to the Future, Part 1, when Marty's in the 1950s, he's talking to Doc Brown about how much power he needs to make his flux capacitor work to go through time, and it's 1.21, and he says gigawatts. It's the other way around. Doc Brown, Christopher Lloyd called it gigawatts because he did not know how to pronounce gigawatts because he's an actor, not a scientist. And in fact, at the time, almost nobody used the phrase giga for anything. The idea that you would ever in common language need to say giga this or giga that was out of the question. No one had heard of this. So I don't fully blame him because it wasn't in the common lexicon at all. So 1.21 gigawatts, meaning 1.21 billion watts of electricity is what it takes to apparently turn on a flux capacitor. Moving on. So files, everything you use in your computer is a collection of bits and bytes. Bytes and gigabytes nowadays. And that's just how much information is in them. It could be your software application files. Sorry, it can be the software itself. It could be the fonts. It could be the application files. It could be images you're using. Everything on your computer is made up of these same building blocks of a base 2. In fact, if anybody goes on and reads the book Humble Pie by Matt Parker, I recommend it. I just finished it. It's quite good. He's the stand-up mathematician who I like to use for like his spreadsheet videos because A, he's fun and entertaining, and B, it's really good and informative math. There are problems on computers where using base 2 math as the basis of what you do causes rounding errors when you're trying to use base 10 numbers that we're more commonly using as humans for things like science and engineering. So especially in things like Excel, which was never meant to do high-end calculations, you can have problems where trying to do a fraction of 0.1 plus 0.4, you guys all know really quickly off the top of your heads, that's 0.5, obviously. Well, sometimes when a calculator or a computer is doing that, those numbers don't translate evenly into binary numbers and come out rounded off a little bit, like it becomes 0.49999999999 ad nauseum. So interesting thing about that. Base 2 math doesn't always work out for translating to regular base 10. They don't always add up. There are corollaries for sure, and some numbers are easy for it to do, but some things are hard. Kind of like in base 10, if you try to divide by 3, 10 divided by 3 is 3 1/3. But when you actually try to do that in decimal, it's 3.333333333. And if you try to put 3 of those together, you should get 10, but you don't. You get 9.999999999 because the rounding and because it wasn't evenly divisible. So you run into those kinds of errors sometimes with programs and with the math being done in programs. So you got to watch out. Computers are very powerful and very useful, but they're not infallible. All right, we're going to pause here and come back to do the second half in just a bit.